All right, guys and ladies. So let's look at the mirror problem. I want to give you a good example. It's in the Spring 15 exam. It's not going to be just like this, but it's a good example of one. And then there are also some in your end of chapter work, and there are some other ones in the old exams, but I don't always give a problem where you have to do the substitution, solving by substitution, but you will have to do it on this coming exam. All right, so on this number 1, this is exam number 4 on Spring 15. I have a mirror that produces an upright image, and then it tells me that the object is 2 centimeters high and the image is 8 centimeters high. So there are several things that I can tell just from that information. The first thing is that it is a virtual image, because virtual images are always upright, right? They're always upright. And then also, I can tell that the image is bigger. And so just from those, I can tell what type of mirror it is. Is it concave or convex? Concave. It's a concave mirror. So those things tell me that it's a concave mirror. We'll come back to that, and I'll review how you tell, based on the image, what type of mirror you have. But knowing your ray diagrams will help you with that. So let's just sort of lay that aside, and we'll come back to that. But because it's concave, I know that it has a positive focal length. So I can tell that the magnification is 8 divided by 2. Right, that's HI over HO. Or actually, on your equation sheet, it calls it something different, I noticed, H prime over H. But it's the height of the image over the height of the object. And so my magnification is equal to 4. And then also, I'm told that the center of curvature is equal to 16. So that means that the focal length is C divided by 2. And so that's equal to plus 8. Now, if it were a convex mirror, it would be negative 8. So you'll need to distinguish, is it concave or convex? And it's positive only because it's concave. I'll ask you actually in the question, what kind of mirror is this? And then I'll also ask you, what kind of image is formed? And I'll expect you to tell me, I give you the language. Is it real or virtual? Is it bigger or smaller? And is it upright or inverted? So I'll ask you those. You'll just circle the words. Is it real or virtual, upright or inverted, or bigger or smaller? If it's upright, right, then it's, well, we'll come back to that. We'll talk about it. Yeah, Lynn?
So that's saying positive underneath the concave?
Yeah, underneath the concave is, yeah, it just sort of slipped my pen a little bit. It's a positive focal length because it's concave. Concave mirrors have a positive focal length. Concave mirrors, the focal length is on the same side as the object. And anytime you have measurements on the same side as the object, that's like the real side of the mirror. This is the virtual side, so we'd have negative values on the back side of that mirror, like with the convex mirror. So that's what I have so far. I have 2 equations, which I'll go ahead and put in what I know here. M is negative Q over P, so 4 is negative Q over P. F is 8, so 1 over 8 is equal to 1 over Q plus 1 over P. I have 2 unknowns, but I have 2 equations, so I can solve that as a system of equations. These are not terribly difficult as far as systems of equations go, but make sure that you know how to solve this kind of thing. I'm looking for where the object is located, so I want to know in this problem what is P. So I'm going to solve that for Q and substitute in Q in the lens equation or the mirror equation. I'm going to say Q is equal to negative 4P. Just cross multiplied. And the reason I solve for Q is because I'm looking for P. So I'm going to take this quantity and plug it in up here so that in this equation I'll only have P, which is what I'm looking for, right? Where is the object located? It could go the other way. If I was looking for Q, then I would solve the magnification equation for P in terms of Q, and then I'd plug that in. You follow what I'm saying? Yeah, no. You have solved systems of 2 equations before. In Algebra 1, you should have in college algebra, but I understand that it might have been some time. But practice, that will help you because you'll want to move pretty quickly through this, especially since you know what to expect. Okay, so I have 1 over 8 equals 1 over negative 4p plus 1 over p. And then this is the other part, is you want to know how to solve this. Find a common denominator, and then you solve for p. So I have 1 over 8 is equal to, what's the common denominator for this, for 4p and p? It's not p, it's 4p. So I'd have 4p in the bottom, negative 1 plus 4. Is that right? Yeah, that's right. So that's negative 1 over 4p and 4 over 4p, which is 1 over p. So that gives me 1 over 8 equals 3 over 4p, and then I solve that for p. 24 is equal to 4p, so p is equal to 6. So the answer here is D, 6 centimeters. So in the course of this question, this is probably your hardest free response question, I would ask you several things. I would ask you what type of mirror is it? What type of image is being formed based on what you know about the mirror and sort of the magnification and the light. And then I would ask you for the magnification, I think I asked for your magnification. And then I also ask you for the object or the image distance. Okay? I know that's a little scary for some of you, just sort of the solving the fractions, doing the substitution, but those are all good skills that you need to have before you leave this course. They'll be useful to you in the future when you're doing various other things. Okay? Yeah. Before we move away from this, let me show you, because it will be very important for this test, that you understand the different mirrors and the different images that they form. So let's review those. Knowing your ray diagrams will help you in that, but just knowing those simple diagrams that I did. Everybody got this okay? Yeah. All right, so for mirrors, we have 4 situations. Right? That's my concave, the 3 concave scenarios. Outside the focal point, at the focal point, inside the focal point, and then the convex, there's really only one scenario because you're always going to be opposite the side of the focal point, since the focal point is on the back side. Remember, with convex, it's a diverging device. It has a negative focal length, while all the others are concave, and they all have a positive focal length. You're going to need, in the free response problem, as I said, you'll need to figure out, based on the image that's being formed, if it's concave or convex. And if you know these 4 diagrams, you'll be able to distinguish them. This one creates an image that is, let's see, I'll do the images in green. How about that? I'll do them in red. There's my image there. This one has no image. And here's my image here. And there's my image there. Okay? This first one is the only one that produces a real image, and it's inverted. It may be upside down, or excuse me, it may be bigger or smaller, or it may even be the same size as the object. The second one produces no image. That's not going to be your one. It'll be one of the other 3. And then the third one is a virtual image. It's upright. Virtual images are always upright in single lens or mirror systems, and it's bigger, right? This is like the makeup mirror, and then this last one is like the security mirror. It's virtual, upright, and smaller. You'll need to know those. You'll need it for the free response. Then you'll also have some multiple choice questions that'll be more conceptual. I might just ask you, hey, if the object is inside the focal point, what kind of image is that? Probably will ask you that. And I'll also ask you, you've seen these before, I'm sure, on the old test where I give you, this is a lens or a mirror, and this is what the object and the image look like. What kind of mirror or lens is this? And you have to choose from 4 options: concave or convex, lens or mirror. Okay? Let me show you the lenses while we're at it. This is going to impact a number of different questions on the test, so kind of important. Lenses, a 3 for convex. So I'm going to make this bigger. And then 1 for concave. Remember, the naming conventions are different. This is convex. Notice it's different from mirrors. And this is concave. The focal points, I have them on both sides for each. Okay? But the types of images are very, very similar. I'll do the objects in the same color as before. And now my images are going to look like this. The images are in red. There's no image here. Here the image looks like that. And here the image looks like that. This is it's real inverted. Just like before, all the images are all the same. No images. Virtual upright big. And virtual upright small. I want you to notice the difference in these, though, is that with lenses, real images occur on the back side of the lens. They occur on the side opposite the object, and virtual images appear on the same side as the object. Because if you think about lenses, this is sort of the normal place where you put a screen, right? On the opposite side of the object, just like with the projector. There's the light source, there's the lens, and then there's the screen. But with mirrors, that's not the case. That you can't put a screen on the back side of a mirror. That's just not how they work. If you put it behind a mirror, they won't do anything. There won't be any light at all. I feel like y'all have those different diagrams. Yeah. Inverted. It can be either. So just like with the mirrors, it depends where you are with respect to the focal point. I know they can be the same size. I think they can be smaller too. I'm not positive with that. Yeah, they can either be big or small or inverted, or the same size. I won't ask you that.
What is this called? Ray diagram?
Yeah, so if you know your ray diagrams, how to draw the ray diagrams, then that will help you to remember these. And you do need to know your ray diagrams. You'll have a couple of questions based on the ray diagrams. I might ask you a question just about the rules. Remember the 3 rules that we have for lenses and mirrors? And then I'll also just give you a ray diagram, and you'll have to identify the rays as either being correct or incorrect. I can show you an example of that. Like, for example, right here. Which one of these rays is drawn incorrectly? This is the spring 15. So this one right here, does my pen work? Yeah. That's parallel to the axis through the focal point. That's okay. This one is through the focal point parallel to the axis. That's okay. This one is through the center of curvature and then parallel to the axis. So ray number 2, not correct. The tricky part is the concave lens, the convex mirror, and then the concave mirror convex lens when you're inside the focal point. So these are particular ones that you should review. You should know them all, but these are the more difficult ones. This one, this one, this one, and this one. They're more difficult because those are the ones where you have to deal with the virtual rays and sort of tracing them back and tracing them forward. That just gets a little more complicated. You still follow the same rules: parallel to the axis and through the focal point and parallel to the axis. And then for mirrors, through the center of curvature and it reflects back on itself. And then for lenses, just straight through the center of the lens. So I might just ask you a question: what are the rules?
No.
Okay.
Yeah. For lenses, why are there 2 objects?
there are two objects.
Where?
Like for lenses, there were like two dots separate.
That means focal points.
Oh no, these are the focal points. The dots here?
Those are focal
Yeah,
points,
those are
not
focal
objects.
points. Yeah, because lenses have two spherical surfaces, and so there's one, like a lens looks like this. So this side right here has a focal point, and then this side right here also has a focal point.
What about concave?
Right, so that has two spherical surfaces too. They're just going the other direction. So these are the focal points here and here. This is the image, and that's the object.
And what do those arrows represent again?
That's the object.
The object, yeah. The arrows are the objects.
The blue one is the object, the red one is the image it produces.
Yeah, the arrows, sometimes I do smiley faces, sometimes I do arrows. You can see either. I'm not sure what I did. I think I did smiley faces. Just to make you happy, right? Because it's good to see somebody smiling during a test, right?
Yeah, the only way to make me happy is to make it where I don't have to take any physics class or organic chemistry ever again.
Oh, organic chemistry, I'll tell you. I've talked to students when they graduate, and they have a complete turn, and they say, organic chemistry, and you know I made a C in that class, and they're like, hey students, but it was the most challenging and gratifying class that I've ever had. Yeah, I mean, you'd be shocked, because I agree, organic chemistry sucks. No. Did I just say that?
Yes, you did.
No.
I'm keeping your word for it.
But,
It's mostly because organic chemistry is so
but it is a good course, and it's very important for your work in the future. All right? Because, you know, if you're in biology, a lot of you are in biology, what are people made of? Organic molecules.
which is so rare in the universe.
Right. Okay? What would y'all like to look at? Now, the other two free response are two. What's that?
The two.
Okay. Yeah, so the other two. The first one that you'll come to on the test is going to be a diffraction grading. And I will tell you, well, let's just look. I mean, on the old test, there are problems like this. So I can find one for you, and we'll just work an example. Might have a few more little pieces attached to it, but no, let's go back. Let's go back to 18. No, we'll go to 17. Okay. I'm going to look at number 9, but I want you to understand that it's not going to be a double slit on your problem. It's going to be a diffraction grading. But double slits and diffraction gratings, they work out identically except for one little step. And then we'll come back later and we'll work that little step in a separate problem. So let's look at number 9 here. This is spring 17. And what I'm given here is the lambda, the wavelength, 650 nanometers. I'm given the slit separation, that's 0.1 millimeters. That is 0.1 times 10 to the minus 3 meters. And then I'm also given the distance to the screen, L, which is going to be 5 meters. Now the one difference in this problem and the one that you'll have is that I won't give you this. I'll give you instead the number of slits per millimeter or centimeter. We'll come back to that. We'll work that problem separately. What I'm going to ask you is how far is, well, actually I'll ask you what this question asks. How far is the second bright fringe from the central maximum? It's probably not going to be the second fringe. It'll be the third or whatever. I don't know. But I know then from that sentence that I'm looking for the second order. So if I'm looking at my system, my diffraction pattern looks like this. The second one is up to there. I'm looking for this distance. What is that distance? So this is the very first question on your test. couple steps you take. First, you find theta. You say d sine theta equals m lambda. And I think I actually break this down into multiple steps so that you do each step separately. And so theta is the inverse sine of m lambda over d. Inverse sine of m, which is 2, lambda, which is 650, times 10 to the minus 9. Don't forget, nano, milli, and centi are the metric prefixes that you'll have to know. And then d is 0.1 times 10 to the minus 3. Those are all in SI units. They have to be in SI units. That is 0.74 degrees. Wait, is that right? Did I do an arc sine? Yeah, that's 0.74 degrees. Okay? So that's my angle theta. And then if I want to find y, I say y is equal to L tan theta, which is going to be 5 times sine of 0.74. And I get 6.5 times 10 to the minus 2, 0.065 meters. And so that's 6.5 centimeters. That's the answer for that one.
So will you give us L?
I'll give you L, yeah. It'll be identical to this problem, except instead of being a double slit, it's going to be a diffraction grading. And in order to find that, let me show you, there's another problem on here. That's that kind of problem. Look at this number 13 over here. Number 13, a diffraction. Oh, a diffraction gradient is 3,000 lines per centimeter. What is the slit spacing? So in order to find that, I would say 1 over 3,000. That's going to be centimeters per line, right? Or I can just say centimeters. It's just the distance between the slits. And that gives me 3.3 times 10 to the minus 4. But that's in centimeters. And so that's going to be 3.3 times 10 to the minus 6 meters. Look, make sure you're good at changing your metric prefixes. Just make sure that you can. It's better if you don't have to go through the whole building the ladder and putting in all the conversion factors, that you can just say, oh, it's centimeters, I'll just move the decimal place over 2 places. Or I would decrease this number by 2 numbers, from 10 to the minus 4 to the minus 6. Sydney? Oh, for what?
The bus, the one you just did. Define y.
Oh, use tangent. Did I write sine? Oh. Sorry about that. That's confusing, isn't it? Yeah. So that's 5 tan of 0.74. Yeah. I think either one, actually. The tan at a small angle like that, the tan of theta is equal to the sine of theta. But not all of our angles are small angles. I know, like I said in the class, that if you're reading the book, they might say, oh, you can just use your small angle approximation, but that doesn't always work, just because I'll use numbers that might not be realistic just because they're simpler numbers. Okay? All right, and then the third free response is a double lens system. And all these are in the old test. So like here's one. It's a 2-lens system. It'll be something like this. Something very, very similar. It will give you a very similar figure. They'll just be different distances, 2 convex lenses separated by a certain distance. And the way you work these is you work them in 2 steps. So there's my optical axis. There's my object. Lens 1, lens 2. This one is 10 centimeters focal point. This one is 15 centimeters. And then this is 20 centimeters from the first lens. and then this is 50 in between. So let's work this. I want to know the magnification of the final image, and then I also want to know what is the image distance. Where is the image located? So I first look at this lens, and I say 1 over f, that's 1 over 10, equals 1 over 20, that's 1 over p, plus 1 over q. And I solve that for q. Look, 1 over 10 is 2 over 20, minus 1 over 20 is just going to be 1 over 20. So q is equal to 20. You'll find that your numbers are going to be similarly simple. So if you can do those without pulling out your calculator, you'll go faster, but you can use your calculator too. So q is equal to 20, and then also my magnification is negative q over p. So that's negative 20 over 20, which is negative 1. So my first image is 20 centimeters. It's inverted, and it's the same size as the object. So this distance is 20 centimeters. I get that from right here. And then the reason I draw it upside down is from that. And the reason I draw it the same size is because of that 1. Now this image becomes the object for the second lens. So I have to first find out this distance. 50 minus 20 is equal to 30. That's going to be my P2. This is my F2. And now I do the whole thing over again. 1 over F2, that's 1 over 15, equals 1 over 30, plus 1 over Q2. So Q2 is equal to 30. This is 2 over 30, minus 1 over 30. Take the inverse of that, that's going to be 30. 30 centimeters. And then M2 is negative Q2 over P2, negative 30 over 30. So this is also a negative 1 magnification. This was M1 over here, M2 for the second lens. To find the total magnification, you just multiply them. So my total is equal to the product of M1 and M2, negative 1, negative 1, positive 1. So my final object is going to be upright, the same direction as my final image is going to be upright. It's going to be the same size as the original object, and it's going to be real. The reason I know it's real is because this is positive. I don't think I asked you this on the free response, but it might come up in your multiple choice to be able to describe those. Also, I want you to describe the position, not just the image distance. So the position of this object, or image rather, is 30 centimeters to the right of the lens. Okay? Because it's a real image, that image has to be over on this side, so it would look like this at a distance of 30 centimeters. That's the third question, and I think there are 2 parts to it. All right? I think there are 3 parts for the diffraction, 3 parts for the mirror problem, and then 2 parts for the lens problem. So 5 total for mirrors and lenses, and 3 for diffraction on the free response. That's 8 questions. I want those to be gimmies. Like, it's a lot easier if everybody gets them exactly right. It's easier for me to grade because I don't even have to just look, oh, they did that right.
I mean, real life doesn't always work out the way you planned.
Well, I'm just asking a favor, really, that you just get them exactly right. Okay? Can y'all do that?
Can't make any promises.
I would love that if everybody would get them exactly right. What? All right. You want to just sort of scroll through some of the old tests, or you have particular old test questions? Remember, as you come to them, if you see anything about sound, you've gone too far.
Experiment.
Single slit experiment? Like this one?
Yeah, single and or double.
Okay, they're all very, very similar. I mean, their equations are a little bit different because the single slit refers to the width of the slit and not the separation of the slits. And the single slit refers to what type of fringes? Dark or bright? Single slit is dark. Dark, dark, dark. But if you go on the equation sheet, let me show you. That can be a key for you. So if I'm looking at the equation sheet, these two, and this is what you'll have on the test. Actually, I did like I did last time, where I just took chapter 7 and 8, and I put them on the front of the bubble form just to save paper. So these two are for our double. This is for diffraction. But notice, this is exactly like the double. And then this is for the single. But once you work a few of them, you'll see that they're very, very similar. They work out the same way. The only thing is that for the single slit, you're looking at your dark spots. But just remember, hey, this says dark, and this says bright, and this says bright. So that can help you. But you need to practice a few of them to make sure that you know how to do them. That's really the thing. Because you have all the formulae, you have everything that you need to work them. You just need to practice them. What do you want to look at?
So what would be a problem of diffraction? What's the word?
I don't know.
That.
The diffraction grading?
Yeah.
The one that I worked just a few minutes ago, so the free response problem. It'll be like that. Okay. So. Oh yeah, those are good. Yeah, so out of phase, in phase kind of thing. Yeah, you'll have, I'll show you, like I said, I'll show you two waves, and I'll ask you how much are these in phase or out of phase. And then I'll also, well, let's just take a look. Well, like number 15 here, right? So make sure that you can do this. It doesn't matter if it's single slit, double slit, diffraction gradient, it doesn't matter. I'm looking at the first order maximum right here, and I want to know how far have the waves traveled to give the minimum, like what is the path length difference have they traveled? In order to get that first order, what is how much are they offset from one another? Remember, if it's a full wavelength, that's constructive interference. If it's a half wavelength, that's destructive interference. And since it's a maximum right here, then I know that it has to be a full wavelength. It's either 0, 1, 2, 3, 4 wavelengths, on and on. So this is going to be what? It's going to be 1 wavelength. So here, I'm offset by 1 wavelength. So as we showed you in class today, this is, how many wavelengths is this? There's 1, there's 2. That's 2 wavelengths. So it's as if I'm starting my next wave right here in order to produce this pattern. It's not as bright as the central fringe because at the central fringe you have 0 wavelengths, and so you have the entire waves that are combining with one another, but it's still a constructive interference. And so it produces a bright spot. Also, let's see if there's one here. Yeah, we did one like this. This is sort of like the mountain problem that we worked. Remember the mountain with the radio station? I have 2 waves of wavelength 4 meters. So the wavelength is 4 meters. And then the first wave travels 8 meters, and the second wave travels 12 meters. And when they meet, what type of interference occurs? Well, the path length difference here is 12 minus 8, which is 4 meters. And so the path length difference in terms of wavelengths is equal to 1 wavelength. We worked one like this in class today. So that's 1 wavelength. So do I get constructive, destructive, or something in between? If I'm 1 wavelength offset, I get constructive, right? So I'm going to get total constructive interference because it is an integer value. If the path length difference was, say, 2 meters, then I would get destructive because notice 2 meters is half of the wavelength. And so that would mean the 2 waves would be offset by a half wavelength, and I would get destructive interference.
So like if you have a fourth, or you don't have to do like a fourth.
Right, if it was something in between, it wasn't a full wavelength or a half wavelength, then the answer would be C. That it's somewhere in between. So on our interference pattern, if it was, say, a fourth or a third or just something in between, then we would find ourselves, somewhere that's not at a peak or a maximum, or a peak or a trough on that diffraction pattern.
If it's not a peak or it's not a value, it's neither total constructive or destructive.
Right. And
It
you'll
has to be at the top, at the very top of the very bottom to be total.
Right. And as I said, that we'll call this, those are all total constructive interference. I know that we talked about, they are offset, and they're technically, this is really technically 360 degrees out of phase, but we'll call it in phase and total constructive interference. Yes.
So if I got this straight, crest to trough is total constructive interference, and destructive interference is crest to crest or trough to trough.
No. So if I have 2 waves that are adding up, like this, where I have the peaks lining up with peaks, if I add those up, those give me a wave like that. Like the whales, right? They created 2 waves where the peaks lined up, but if I have 2 waves like this, and I add those up, those give me destructive interference. Like your noise-canceling headphones that one of our students had. Okay? What else, y'all?
You said the wavelength as, you said an integer wavelength?
Yeah.
That's
Constructive, yeah. So if we're 1 full wavelength, or 2 full wavelengths, or 3 full wavelengths, that's going to be constructive interference. But if we have a half a wavelength, a half, 1.5, 2.5, 3.5 wavelengths, that would be destructive interference.
And then anywhere between the halves and the integers
Would be something else. Yeah.
So what would a neither total or constructive interference look like?
Like for example, if say the path length difference I don't know, say 3 meters. Right, 3 meters is not a half of the wavelength. It's actually 3/4 of the wavelength. So this is equal to 3/4 of the wavelength, and so that's neither constructive nor destructive. That would actually be what 135 degrees out of phase, I guess.
what is the wavelength get bigger or smaller?
The wavelength would stay the same. So just what do you mean?
Yeah. One wavelength and then another one 3/4 out of phase. Does the whenever they combine?
Oh, let's see. So at 3/4 of a wavelength, you would be sort of, what's that? You'd be like right about here. So you get because this is a half a wavelength, right? And this is 1 wavelength. So you'd be somewhere in between those two.
So it would be a quarter of so if half difference was divided by the wavelength, and if you have a quarter, then it would be neither.
Right. Right. Or so it's not a half and not a full integer. It's not neither constructive nor destructive. Anything else other than 1 or an integer or a half, 1.5, 2.5, 3.5. Okay? Let me scroll through these. I have a seminar at 4, so I'm going to have to wrap up in about 5 minutes. Or if you have particular questions, now's the time to ask them. Oh, there's a lot of lens equations. So yeah, Tristan.
Look at number 16.
On this one?
Yeah.
There's a lot of lens equations, so make sure that you that you're up on solving the lens equation. Okay? There's probably 3 in the multiple choice. There's probably 3 questions, I think, that are either the lens or mirror. It's just because it occurs twice for both mirrors and lenses. So, and then when you add in the free response, man, you're going to be solving that lens equation 5, 6 times. So make sure that you're fast at doing that, because fractions, people sort of freak out over fractions, but you can do it. It's, you know, it's middle school math, but it's been a while. I understand since you've done it. Number 16, you'll see one like this too, okay? It might be single slit, it might be double slit, it might be diffraction grading, but they all work the same way. So here, it's a single slit, so I just immediately write down this. All right, and if I increase the wavelength, what happens to the width of the central bright fringe? Well, this is my wavelength, and when I talk about the width of the central bright fringe, you might be inclined to say that that's A, but that's not A. A is the width of the slit. The width of the central bright fringe is this width, right? And that width is given by this angle. So it's proportional to that angle. So anytime you see the width of the fringe, you're thinking, what's happening to the angle theta? And if I increase the right-hand side, I have to increase the left-hand side. So theta is going to increase, which means that the slit, or not the slit, the fringe will get wider. Then if I increase the wavelength, my fringe gets wider. That was true today. Remember I showed you the diffraction grading, and you saw the red and the green? The green, the dots were closer together. The red, they were farther apart. That's because I increased the wavelength when I went from green to red. It's quite a bit longer, the red wavelength. Roy G. Biv, right? That R has a longer wavelength than green. You will see one like that. It might not be single slit, it might be double slit or diffraction grading, but they work out the same.
Even if it is, so even if it's whether it's single slit or double slit, we do the same. We work the same way.
Right. You just write down the equation for single or double or diffraction gratings. It's a double slit and diffraction gratings have the exact same equation. Single slit's just got an A instead of a D. Alrighty? Is that all? Alright, let me tell this. Don't leave until I get your name marked down, okay?